Okay, in this problem we have a frictionless scooter and it's moving around a 45-degree banked turn with a radius of 3 meters, and we're to find its velocity as it makes that turn. My suggestion for solving these problems is when you draw your initial free body diagram to analyze the forces, draw the body that's moving around on the banked corner as a single dot. It makes the geometry a whole lot simpler. So here we have a cross-sectional view of our banked curve. So the scooter's going this way and then out. It's turning around a radius of 3 meters, and the scooter is on this corner, which has an angle of 45 degrees. Gravity is obviously pulling the scooter straight down. So let's say the scooter's mass is m. Gravity is equal to m times g, g being 9.8. It's just easier to write g. The surface of this banked corner is going to exert a normal force in this direction here. I'll call that Fn. And Fn is perpendicular to the surface. Now, for the scooter to go around a corner, it's going to have to accelerate towards the center of the turn radius. As it curves around here, so on your sheet, I gave you a top view. So here's the top view. This is the lower end of the bank, the higher end of the bank. And as they turn, they're going around a circle. So imagine a center to the circle, and they're traveling this curve. And the radius of that's given here is 3 meters. But we'll solve this in the general case, so I'm going to solve it as if it's r, and then we can plug in the value after. As they make that turn, they must accelerate towards the center of that. I'm assuming you've done uniform circular motion if you're looking at this problem. So they're accelerating towards the center. That means that a component of the normal force, which is going towards the center, is of interest. So this, I'm going to call this FNH for horizontal. So this is the horizontal component of our normal force. And then upward, we're going to have FNV for vertical. So we have a horizontal component and a vertical component of our normal force. The vertical component of our normal force is equal to mg. I know that because gravity is pulling the body down, and the normal force is the only force that's pushing it back up. And this body is neither accelerating upward nor downward, so it must be balanced. So the normal force's vertical component is equal to the force of gravity. Now, the normal force's vertical component is equal to the normal force times the cosine of this angle here. So if this is theta, then this is also theta. If you're not sure why, look for a Z pattern. You see, if this is theta here, we have a Z pattern as this horizontal component is parallel to the ground, and this line here intersects them both. We call it a traverse, I believe. So if this is angle theta, this will also be angle theta. And if this is angle theta, this is 90 minus theta. And if this is 90 minus theta, then this is theta. So the angle here is going to be equal to the angle up here. So with that, the normal force times the cosine of theta is equal to our vertical component of the normal force, and that's equal to mass times gravity, which means that the normal force is equal to mass times gravity divided by the cosine of theta. Now, this is a new idea, because if you pay close attention, you'll see that the cosine of our angle has to be less than 1, meaning our normal force has to be greater than the force of gravity. In the inclined plane problems you've done before the banked corner, quite typically we're in a situation where you take the force of gravity and it's not moving, or if it is moving, it's moving up or down the plane. You take the force of gravity, you find the perpendicular component to the force of gravity, and that ends up being equal to the normal force. This is in previous problems, so this is the perpendicular component of gravity, and it's equal to the normal force in these cases where you have a body sliding up or down. However, this case is very different from that. It's different from that because as we go around a banked corner, that banked corner is curved. That curve, for it to move around that curve, it must accelerate towards the center. And what that means is you must have a value of the normal force greater than the force of gravity, causing that acceleration. See, this body is not staying still. It is moving, and it's moving around a curve. So you must have a normal force greater than acceleration. So be very careful, be slow and careful on this part, and don't go into autopilot. In a problem where a body is staying still on a ramp or sliding up or down, you would have the normal force, and let's say this is theta, so then that'll be theta there. The normal force would be Fg times the cosine of theta. That's if it's sitting still on a ramp or sliding up and down. But if we're going around a banked corner, it's different. And around a banked corner, the normal force is equal to the force of gravity divided by the cosine of theta. Okay, so once you're past that part, it's a very simple problem. See, from here on in, we've got that the normal force's horizontal component is going to simply be the normal force times the sine of theta, which makes it the normal force times the sine of theta. That was useless. I just wrote the same thing again. And that is equal to m times g divided by cos theta times sine theta. And that's just a simple trig identity. This is mg tan theta. So the force that the banked corner will exert towards the center is going to be equal to mg tan theta. Notice that is your centripetal force. This is going around a circle. So the centripetal force is equal to mg tan theta. That is the only force that's acting in this direction. Okay, so with a centripetal force of mg tan theta, we've got centripetal acceleration is v squared over r, and force is mass times acceleration. So that means that the centripetal force is m times v squared over r, but we found it to be mg tan theta. So that means that m times v squared over r is equal to mg tan theta. V squared is equal to r times g times the tan of theta, making the velocity of Theo on the scooter equal to the square root, that could be plus or minus because this would also work if he was going backwards, rg tan theta. And then looking back at our original question, theta is 45 degrees, r is 3 meters, and g, because we're on the Earth, is 9.8 meters per second squared. So that makes this the square root of 3 times 9.8 times the tan of 45. Which is 5.4 meters per second. And to make that a little more understandable, we'll multiply it by 3.6, and that is 19.5 kilometers per hour. Okay, so to recap, when you're doing a banked corner problem, so here it really took 2 diagrams to get the idea. This is the cross section of the banked corner. This is the top view of the banked corner. You analyze it in a very similar way to previous problems. So you draw out the angle of the bank, draw the body as a dot, makes the geometry a lot easier. But remember here, the difference is the force of gravity pulls down. That's not new. The normal force is, of course, 90 degrees from the banked surface. That's what normal means, by the way. But what we're interested in here is the horizontal and vertical component. And the vertical component of the normal force is equal to gravity. In the previous questions, where a body is staying still or sliding up and down a ramp, in those cases, the perpendicular component of gravity was equal to the normal force. But in this case, it is the vertical component of the normal force that's equal to gravity. Difference being here, remember, this body is not staying still, and this surface is not really a flat surface. It is a curved bank, and the body is making its way around the corner.